Accelerated warming and emergent trends in fisheries biomass yields of the world's large marine ecosystems. Information on the effects of global climate change on trends in global fisheries biomass yields has been limited in spatial and temporal scale. Results are presented of a global study of the impact of sea surface temperature, SST, changes over the last 25 years on the fisheries yield of 63 large marine ecosystems, LMEs, that annually produce 80% of the world's marine fisheries catches. Warming trends were observed in 61 LMEs around the globe. In the 18 of the LMEs, rates of SST warming were 2 to 4 times faster during the past 25 years than the globally averaged rates of SST warming reported by the Intergovernmental Panel on Climate Change in 2007. Effects of warming on fisheries biomass yields were greatest in the fast-warming northeast Atlantic LMEs, where increasing trends in fisheries biomass yields were related to zooplankton biomass increases. In contrast, fisheries biomass yields of LMEs in the fast-warming, more southerly reaches of the northern Atlantic were declining in response to decreases in zooplankton abundance. The LMEs around the margins of the Indian Ocean, where SSTs were among the world's slowest warming, revealed a consistent pattern of fisheries biomass increases during the past 25 years. Driven principally by human need for food security from fisheries resources. As a precautionary approach towards more sustainable fisheries utilization, management measures to limit the total allowable catch through a cap and sustain approach are suggested for the developing nations recently fishing heavily on resources of the Agulhas Current, Somali Current, Arabian Sea, and the Bay of Bengal LMEs. Introduction. The heavily exploited state of the world's marine fisheries has been well documented. Little, however, is known of the effects of climate change on the trends in global fisheries biomass yield. The fourth assessment report of the Intergovernmental Panel on Climate Change, IPCC, stated with high confidence that changes in marine biological systems are associated with rising water temperatures, affecting shifts in pelagic algae and other plankton, and fish abundance in high latitude. The report also indicated that adaptation to the impacts of increasing temperatures in coastal systems will be more challenging in developing countries than in developed countries because of constraints in adaptive capacity. From a marine resources management perspective, the 8 regions of the globe examined by the IPCC, that is North America, Latin America, Europe, Africa, Asia, the Australia and New Zealand region, and the 2 polar regions, are important fisheries areas but at a scale too large for the determination of temperature trends relative to the assessment and management of the world's marine fisheries biomass yields produced principally in 64 large marine ecosystems. These LMEs in coastal waters around the globe annually produce 80% of the world's marine fisheries biomass. LMEs are areas of an ecologically based nested hierarchy of global ocean biomes and ecosystems. Since 1995, LMEs have been designated by a growing number of coastal countries in Africa, Asia, Latin America, and Eastern Europe as place-based assessments and management areas for introducing an ecosystems approach to recover, develop, and sustain marine resources. The LME approach to the assessment and management of marine resources is based on the operationalization of 5 models, which suits of indicators for monitoring and assessing changes conditions in ecosystems. Number 1 being productivity, 2 fish and fisheries, 3 pollution and ecosystem health, 4 socioeconomics, and 5, governance. The approach is part of an emerging effort to relate the scale of place-based ecosystem research and assessment to improved ecosystem-based management of ocean resources within the natural boundaries of LMEs. In recognition of the observational evidence of global warming from the 4th assessment report of the IPCC and the lack of information on trends in global warming at the LME scale, where most of the world's marine fisheries biomass yields are produced, we undertook a study of the physical extent and rates of sea surface temperature trends in relation to fisheries biomass yields and satellite-derived primary productivity of the world's LMEs. Methods. Fisheries biomass yields are not presented here as representative of individual fish stock abundances. They are representatives of fisheries catches and are used here to compare the effects of global warming on the fisheries biomass yields of the world's LMEs. The comparative analysis of global temperature trends, fisheries biomass yields, and primary productivity was based on available time series data at the LME scale on SSTs, marine fishery biomass yields, and sea viewing wide field of view sensors. CWIFs. Derived primary productivity values. The SST of LMEs is a thermal parameter routinely measured worldwide. Subsurface temperature data, albeit important, are limited in the spatial and temporal density required for the reliable assessment of thermal conditions at the LME scale worldwide. The UK Meteorological Office Hadley Center SST climatology was used in this analysis, as the Hadley dataset has a resolution of 1 degree latitude by 1 degree longitude globally. A detailed description of this data set has been published by Rayner et al. Mean annual SST values were calculated for each 1:1 cell and then were area averaged within each LME. LME primary productivity estimates were derived from satellite-borne data of the National Oceanic and Atmospheric Administration's Northeast Fisheries Science Center, Narragansett Laboratory. These estimates originated from CWIFs, satellite-derived chlorophyll estimates, coastal zone color scanner CZCS, a large archive of in-situ near-surface chlorophyll data, and satellite SST measurements to quantify the spatial and seasonal variability of near-surface chlorophyll. Near-surface chlorophyll and SST in the LMEs of the world. Daily estimates of global primary productivity G carbon m to the power minus 2 d to the power minus 1 were calculated using the ocean productivity from absorption and light model, a derivative of the model first formulated in Mara et al. Prior to the Sea Around Us project, SAUP, projections of marine fisheries yields at the LME scale were largely defined by the range of vessels exploiting a given resource. The need for countries to manage fisheries within exclusive economic zones under United Nations Convention on the Law of the Sea initiated efforts to derive fisheries yield at the national level and is consistent with the emergence of ecosystem-based management at the LME scale. The time series of fisheries biomass yields used in this study was based on the time series data provided at the LME scale by the SAUP at the University of British Columbia. Result: Comparative SST cluster. The 1957 to 2006 time series revealed a global pattern of long-term warming. However, the long-term SST variability since 1957 was not linear over the period. Specifically, most LMEs underwent a cooling between the 1950s and the 1970s, replaced by rapid warming from the 1980s until the present. Therefore, we recalculated linear SST trends using only the last 25 years of data. Net SST change in each LME between 1982 and 2006 based on linear SST trends is summarized in Table 1. The most striking result was the consistent global-scale warming of LMEs, with the notable exception of two, the California Current and Humboldt Current. These LMEs experienced cooling over the last 25 years. Both are in large and persistent upwelling areas of nutrient-rich cool water in the eastern Pacific. The Arctic Ocean LME was not included of perennial ice cover. The SST values were partitioned into 0.3 degrees Celsius intervals to allow for comparison among LME warming rates. The warming trend observed in 61 LMEs ranged from a low to 0.08 degrees Celsius for the Patagonian Shelf LME to a high of 1.35 degrees Celsius in the Baltic Sea LME. The relatively rapid warming exceeding 0.6 degrees Celsius of over 25 years was observed almost exclusively in moderate and high latitude LMEs. This pattern is generally consistent with the model predicted polar and subpolar amplification of global warming. The warming in low latitude LMEs was several times lower than the warming in high latitude LME. The most rapid warming, exceeding 0.9 degrees Celsius over 25 years, was observed in the Baltic Sea, North Sea, East China Sea, Sea of Japan/East Sea, Newfoundland Labrador Shelf, and Black Sea LMEs. The 18 fast and superfast warming LMEs net change over 0.6 Celsius between 1982 and 2006 were warming at rates approximately 2 to 4 times higher than the IPCC 2007 global average SST warming rate of 0.133 plus minus 0.47 degrees Celsius decade to the power minus 1. Primary productivity. The importance of primary productivity in supporting the bottom-up trophic links to fisheries productivity is well known. No large-scale consistent pattern of either an increase or a decrease in primary productivity was observed. Of the 64 LMEs examined, only 4 of the productivity trends were significant. E is less than 0.05. Primary productivity declined in the Bay of Bengal and increased in the Hudson Bay, Humboldt Current, and Red Sea LMEs. The general declining trend in primary productivity with ocean warming reported by Behrenfeld et al. Was limited to the Bay of Bengal LME. No consistent statistically significant trend among the LMEs was observed. However, in previously reported fisheries biomass yields did increase with increasing levels of primary productivity in all 63 LMEs. Fisheries biomass yield trends. The effects of warming on global fisheries biomass yields were non-uniform in relation to any persistent global pattern of increasing or decreasing yields. The relationship between the change in LME yield and SST change was not significant. The slight suggestion of a trend in the regression was influenced by the data for the Humboldt LME. Partitioning of the results into LMEs with increasing trends in fisheries biomass yields and those with declining trends divided the trends into 2 groups. Increasing yields were observed in 31 and decreasing trends in 32 LMEs. Differences were similar in fast warming, 8 increasing, 10 decreasing, and in moderately warming LMEs, 10 increasing, 8 decreasing. In the slower warming LMEs, most 14 were undergoing increasing biomass yields and 6 were in a decreasing condition. Linear warming trends from 1982 to 2006 for each LME were distributed in distinct global clusters. 1. The fast-warming LME clusters were in the Northeast Atlantic, African, and Southeast Asian waters. 2. The moderately warming LMEs were clustered in the Atlantic and North Pacific waters. And 3. The slow-warming LME clusters were located principally in the Indian Ocean and in locations around the margins of the Atlantic and Pacific Oceans. Comparisons of fisheries biomass yields trends for 11 LME warming clusters were examined. Comparative fisheries biomass yields in tons in fast-warming European LMEs. In the Norwegian Sea, Faroe Plateau, and Iceland Shelf, the fisheries biomass yields was increasing. These three LMEs accounted for 3.4 million tons, or 5% of the world biomass catch. This cluster of LMEs was influenced by bottom-up forcing, the increasing zooplankton abundance, and warming hydrographic conditions in the northern areas of the North Atlantic, where stocks of herring, blue whiting, and capelin were benefiting from an expanding prey field of zooplankton, supporting growth and recruitment of these three species. The warming trend in the Norwegian Sea, driving the increase in the biomass of herring, capelin, and blue whiting yields, has been reported by Skjotdal and Sætre. On the Faroe Plateau LME, Gard et al. Indicated that the increasing shelf production of plankton is linked to the increased production of fish and fisheries in the ecosystem. Astolfsson and Williamson have shown that variations of zooplankton in Icelandic waters are greatly influenced by large-scale climatic factors, and that warm Atlantic water inflows favor zooplankton, which supports larger populations of capelin that serve as an important prey of cod. The productivity and fisheries of all three LMEs were benefiting from the increasing strength of the subpolar gyre, bringing warmed water to the LMEs of the region, generally in the northern Northeast Atlantic, and contributing to decreasing production and fisheries yields in the relatively warmer southern waters of the Northeast Atlantic. In southern Europe, three LMEs in fast-warming clusters of the North City Celtic Biscay and Iberian coastal LMEs were experiencing declines in biomass trends, representing 4.1 million tons, 6.4% of the mean annual global biomass yield. It has been reported that zooplankton abundance levels in the three LMEs are in decline, reducing the prey field for zooplanktivores. Although we did not detect any significant decline in primary productivity in the three LMEs, the declining phytoplankton level in the region was consistent with the declines in primary productivity in warming ocean waters reported by Barenfeld et al. And subsequent expected reduction in fisheries productivity. The fisheries biomass yields of 80% of the targeted species were in an overexploited or fully exploited condition, suggesting that the observed decline in biomass yield of pelagic species was related to both heavy exploitation and warming. The three semi-enclosed European LMEs, the Mediterranean, the Black Sea, and the Baltic Sea, and the adjacent area of the Red Sea, are surrounded by terrestrial areas and are fast warming, with heavy fishing as a dominant feature. The four LMEs contributed 2.4 million tons, 3.7% of the mean annual global biomass yield in three European LMEs. The fisheries biomass trend was decreasing, while in the Red Sea it was increasing. In the case of the Black Sea, the fisheries biomass was severely depleted, with 85% of fisheries stock overexploited due to heavy fishing and a trophic cascade. In the Baltic Sea, Red Sea, and Mediterranean Sea LMEs, 78% of the stocks were in a fully exploited condition. Mixed species dominated in the Red Sea, where 88% of the species fished were fully exploited and 10% were overexploited. It appears that heavy exploitation was the dominant driver of the biomass trends observed in all four LMEs. Comparing fisheries biomass yields in tons in other fast-warming clusters. The three LMEs in the Northwest Atlantic region contributed 1.1 million tons, 1.7% to the global biomass yield. In two LMEs of the Northwest Atlantic, the downward trend in fisheries yield has been attributed to the cod collapse in the Newfoundland Labrador shelf and to the cod collapse and the collapse of other demersal fisheries in the Scotian Shelf LME from excessive fishing mortality. In the West Greenland Shelf LME, where the cod stock has collapsed from excessive fishing mortality, there has been a recent increase in the landings of shrimp and other species. Biomass yields of the fast-warming LMEs of East Asian seas. 7.5 million ton biomass yields of the Yellow Sea and East China Sea LMEs constitute 11% of the global yield. In both LMEs, yields were increasing. The principal driver of the increase was food security to accommodate the needs of the People's Republic of China and the People's Republic of Korea. Biomass yields were dominated by heavily fished mixed species. 70% or more of the species constituting the yields were fully exploited or overexploited, suggesting that the principal driver of increased biomass yields was full exploitation rather than global warming. The fast-warming Kuroshio Current and Sea of Japan, or East Sea LMEs, showed declining fisheries trends. They contributed 1.9 million tons, 2.9% to the global marine fisheries yield. For these two LMEs, exploitation levels were high, with 90% of the species in a fully exploited to overexploited condition. Table 4. The fisheries are also subject to periodic oceanographic regime shifts that affect the abundance of biomass yield. Among the fast-warming East Asian seas LMEs, no analysis was conducted for the ice-covered Chukchi LME, as the data were limited and of questionable value. Comparative fisheries biomass yields in tons in moderately warming Atlantic LMEs and Asia-Pacific regions. A large cluster of moderately warming LMEs were found in the trade winds region of the Atlantic Ocean. This important cluster of LMEs contributed 5.1 million tons, 7.9%, to the mean annual global biomass yield. 5 LMEs were clustered in the Western Atlantic and 2 in the Eastern Atlantic. In the Western Atlantic Ocean, the Gulf of Mexico, LME fisheries biomass yields were decreasing, while in the Caribbean, North Brazil, East Brazil, and South Brazil shelf LMEs fisheries biomass yields were increasing. The fisheries biomass yields trends in the Atlantic Ocean region appeared to be driven principally by heavy exploitation rather than climate warming. The Caribbean, North Brazil, and East Brazil shelf LMEs were in a fully exploited and overexploited fisheries condition equal to or greater than 88% of the stocks. In the South Brazil shelf, 60% of the fisheries were fully exploited or overexploited. The East Brazil shelf and South Brazil shelf LMEs were dominated by small pelagic and or mixed species. The two LMEs of the Eastern Atlantic are important sources of food security to the over 300 million people of West African countries adjacent to the LMEs. The Canary current and the Guinea current showed increasing trends in biomass yield with mixed species dominant. The fishery stock in both LMEs were at risk. Oceanographic perturbations are also a source of significant variability in biomass yields in the Guinea current and in the waters of the Canary current LME. Three LMEs, the Sea of Okhotsk, the Oashio current, and the West Bering Sea, contributed 2.3 million tons, 3.5%, to the mean annual global biomass yield. They were in a condition where 78% of the fishery stocks were overexploited. The Oashio current and the West Bering Sea LMEs showed decreasing trends in fisheries yield. In the Sea of Okhotsk, the biomass yields are dominated by targeted tablefish, including pollock and cod. The increasing yield trend in the Sea of Okhotsk LME was related principally to a high level of overexploitation. Comparing fisheries biomass yields in other moderately warming LMEs. The three moderately warming LMEs, two on the east coast of Australia, northeast and east central Australia LMEs, and the New Zealand shelf LME contributed 0.4 million tons, 0.7% to the mean annual global biomass yield. Biomass yields were decreasing in the Australian LMEs, whereas they were increasing in the New Zealand shelf LMEs under a condition of full exploitation. Whether their conditions were the result of top-down or bottom-up forcing is not clear. However, individual transferable quota (ITQ) management to promote the recovery and sustainability of high-priority fishery stocks was in place. Stewardship agencies in Australia and New Zealand have implemented management actions for the recovery and sustainability of the overexploited species. 6 moderately warming LMEs occurred in separate locations. Taken together, they contributed 7.7 million tons, 11.8%, to the mean annual global biomass yield. In the Pacific, landings were too low in the moderately warming insular Pacific Hawaiian LME to draw any conclusion on biomass yield. In the moderately warming Gulf of Alaska LME, the overall 25-year fisheries biomass trend was decreasing. However, this LME showed evidence of a relatively recent upturn in yield, attributed to increases in the biomass of Alaska pollock and Pacific salmon populations in response to climate warming. The biomass of the moderately warming Gulf of California LME was in a declining trend. The dominant biomass yield in this LME was from small pelagics and mixed species, suggestive of top-down fishing as the principal driver of the decline. The South China Sea fisheries biomass yields were increasing. The dominant biomass yield of the LME was of mixed species and the level of exploitation was high, with 83% fully exploited and 13% overexploited. In this case, the high population demand for protein by the adjacent countries contributed to driving the biomass yield upward. The Arctic region's Beaufort Sea LME landings data were unavailable. The moderately warming East Greenland shelf fisheries biomass yields were increasing with capelin, redfish, and shrimp dominant, following the earlier collapse of cod and other demersal species. The role of global warming in relation to the cause and effect of increasing yields is not known. Comparative fisheries biomass yield in slow-warming Indian Ocean and adjacent LMEs. The 10 LMEs of the Indian Ocean, Arabian Sea, Bay of Bengal, Indonesian Sea, Agulhas Current, Somali Current, North Australia, West Central Australia, Northwest Australia, Southeast Australia, and Southwest Australia LMEs were in the slow range of climate warming, and their biomass trends were all increasing. This group of LMEs contributed 8.6 million tons or 13.2% of the global biomass yield. The slow warming was consistent with the IPCC forecast of slow but steady warming of the Indian Ocean in response to climate change. While biomass yields were increasing, the landings adjacent to developing countries were composed primarily of mixed species and small pelagics, and the stocks were predominantly fully exploited and/or overexploited, suggesting that top-down fishing was the predominant influence on the condition of biomass yield. In the adjacent Southwest Pacific waters, the slow-warming Sulu Celebes and Gulf of Thailand LMEs contributed 1.8 million tons, 2.8% to the mean annual global biomass yield. The consistent pattern of increasing yields of the Indian Ocean LMEs adjacent to developing countries was driven principally by the demand for fish protein and food security. In the case of 5 LMEs adjacent to Australia, the national and provincial stewardship agencies were promoting stock recovery and sustainable management through ITQs. The fisheries stocks in the LMEs adjacent to developing countries are under national pressure to further continue the expansion of the fisheries to provide food security for the quarter of the world's population that inhabits the region. Given the demands on fisheries for food security for the developing countries bordering the Indian Ocean, there is a need to control biomass yields and sustain the fisheries of the bordering African and Asian LMEs. The biomass yields of other slow-warming LMEs. There was slow warming taking place in the Northeast U.S. shelf and in the Southeast U.S. shelf. The LMEs contributed 1 million ton, 1.6% to the mean annual global marine biomass yield. For both LMEs, the declines are attributed principally to overfishing. For these two LMEs and the Gulf of Mexico, the Gulf of Alaska, the East Bering Sea, Chukchi Sea, Beaufort Sea, Insular Pacific, Hawaiian Islands, and the Caribbean, the United States has underway a fisheries stock rebuilding program for increasing the spawning stock biomass of overfished species. Biomass yields of the slow-warming LMEs of the Arctic region. For several of the slow-warming LMEs bordering the Arctic, including the Laptev Sea, Kara Sea, East Siberian Sea, and Hudson Bay, biomass yield data were incomplete and not included in the trend analysis. In the case of the Parent Sea LME, there was a decreasing biomass trend attributing to the overexploited condition of many fish stocks inhabiting the LME. During the present warming condition, variability in ice cover has an important influence on biomass yield. Biomass yields of other LMEs. For widely separated LME, the East Bering Sea, the Patagonian Shelf, Benguela Current, BCLME, and the Pacific Central LME were located in slow-warming waters. Together, they contributed 3.3 million tons, 5.1% to the mean annual global biomass yield. In the North Pacific Ocean, the slow-warming East Bering Sea and an overall decline in fisheries biomass yield. However, in recent years, there has been an upturn in yield attributed to climate warming and increase in the biomass of Alaska pollock and Pacific salmon populations. In the Southwest Atlantic Ocean, the increasing biomass yields of the Patagonian Shelf LME were reflective of a very high level of fisheries exploitation, overshadowing any climate change effects. 30% of fisheries were fully exploited and 69% were overexploited. The increasing biomass trends of the Pacific Central American coastal LME were the result of high levels of exploitation, driven principally by the need for fish protein and food security of the adjacent developing countries, and secondarily by oceanographic regime shifts. The biomass yields of the BCLME, southwest of African coast, were in a declining trend. The living resources of the BCLME have been stressed by both heavy exploitation and environmental perturbations during the past 25 years. The trend of the southwestward movement of pelagic fish, sardine, and anchovy populations from the west coast of South Africa around to the southeast coast has been attributed to recent warming. This has also led to a decrease in the availability of the small pelagic fish prey of African penguins in the vicinity of island colonies, resulting in a 40% penguin population decline. Discussion. Emergent trends from the analysis. We conclude that in 4 LME cases, the warming clusters of LMEs are influencing 7.5 million tons, or 11.3% of the world's fisheries biomass yields. The first and clearest case of an emergent effect of global warming on LME fisheries yields is in the increasing biomass yield of the fast-warming temperature clusters, affecting 3.4 million tons, 5% of global yields for the Icelandic Shelf, Norwegian Sea, and Faroe Plateau LMEs in the northern Northeast Atlantic. Warming in this region has exceeded levels expected from entering the warm phase of the Atlantic multi-decadal oscillation. The increase in zooplankton has been related to warming waters in the northern area of the Northeast Atlantic, leading to improved feeding conditions for 3 zooplanktivorous species that are increasing in biomass yield. Herring, blue whiting, and capeling yields are increasing in the Iceland Shelf and Norwegian Sea LMEs, and blue whiting yields are increasing in the Faroe Plateau LME. The second case is in the contrasting declines in biomass yields of the fast-warming cluster of more southern Northeast Atlantic waters, including the North Sea, the Celtic Biscay Shelf, and Iberian coastal LMEs, where declines in warm water plankton and the northward movement of fish are negative influences on 4.1 million tons, 6.3% of the mean annual global biomass yield. Recent investigations have found that SSD warming in the Northeast Atlantic is accompanied by increasing zooplankton abundance in cooler, more northerly areas and decreasing phytoplankton and zooplankton abundance in the more southerly, warmer regions of the Northeast Atlantic in the vicinity of the North Sea, Celtic Biscay Shelf, and Iberian coastal LMEs. Due to tight trophic coupling, fisheries are adversely affected by shifts in distribution, reduction in prey, and reduction in primary productivity generated by strong thermocline stratification inhibiting nutrient mixing. In the third case, recent moderate warming of the Gulf of Alaska and slow warming of the East Bering Sea are supporting increasing levels of zooplankton production and recent increasing biomass yields of Alaska pollock and Pacific salmon. The biomass yields of the fourth case are more problematic. Biomass yields of all 10 LMEs, 8.6 million tons or 13.2%, around the western and central margin of the Indian Ocean were increasing. The increasing yields of the 5 LMEs adjacent to developing countries, the Gulf Current, Somali Current, Arabian Sea, Bay of Bengal, and Indonesian Sea LMEs were dominated by mixed species and small pelagic species, driven by the fish protein and food security needs of nearly 1/4 of the world's population, which inhabits the bordering countries of Africa and Asia. The overexploited condition of most species is at present masking any gains in biomass yield that may be attributed to the slow and steady warming of waters predicted for the Indian Ocean by the IPCC and observed during the present study. In contrast, the slowly warming 5 Australian LMEs on the eastern margin of the Indian Ocean are driven principally by economic considerations and are closely monitored by governmental stewardship agencies that practice an adaptive management system of ITQs. Taken together, the 8.6 million ton mean annual biomass yield of the Indian Ocean LMEs is critical for the food security of the heavily populated adjacent countries. Recent analysis indicate a growing increase in ecosystem overfishing and loss in fisheries production in the Arabian Sea and the Bay of Bengal LMEs. In this region, there is a need to exercise a precautionary approach to recover and sustain the fisheries in the LMEs of Eastern Africa and Asia in the slow warming clusters. Precautionary cap and sustain action. From a global perspective, 38.2 million tons or 58% of the mean annual 2001 to 2006 biomass yields are being produced in 29 LMEs adjacent to developing countries. This vital global resource is at risk from serious overexploitation. Given the importance of sustaining 58% of the world's marine fisheries biomass yield, it would be prudent for the Global Environment Facility supported LME assessments and management projects to immediately cap the total biomass yield of the annual 5 years mean 2004 as a precautionary measure and move toward the adoption of more sustainable fisheries management practices. Application of the capping of fisheries yields as a precautionary action is especially important during a period of climate-induced changes, when nonlinear changes in fish stock abundance are difficult to predict. The management strategies for protecting the 26.8 million tons of 42% of global marine biomass yields in LMEs adjacent to the more developed countries have had variable results ranging from highly successful fisheries biomass yield recovery and sustainability actions for stocks in LMEs adjacent to Australia, New Zealand, the United States, Norway, and Iceland to the less successful efforts of the European Union and LMEs under EU jurisdiction in the Northeast Atlantic. An ecosystem-based cap and sustain adaptive management strategy for ground fish based on an annual overall total allowable catch (TAC) level and agreed upon tax for key species is proving successful in the management of the moderately warming waters of the Gulf of Alaska LME and the slow warming East Bering Sea LME. Alaska pollock and Pacific salmon stocks providing evidence that cap and sustain strategies can serve to protect fisheries biomass yields. In the absence of the capacity for conducting annual assessments of a large number of marine fish species in many developing countries, and in recognition of the uncertainties of climate warming effects in the observed slow warming and increasing fisheries biomass yields of LMEs adjacent to East Africa and South Asia along the margins of the Indian Ocean, it will be prudent for the bordering countries to implement precautionary actions to protect present and future fisheries yield with a cap and sustain strategy aimed at supporting long-term food security and economic development needs.